Okay, so we want to prove this proposition here. First of all, let me say one more comment about why bounded distortion is a non-trivial fact. So, if you look at a map like this, like the Gauss map, or if you just take any piecewise affine map and you just perturb it so that it's not piecewise affine, so that it's C1 plus epsilon, but the derivative is not constant, then the derivative will be different at different points, of course, okay? And the question is, as we iterate, again, by the chain law, right? If you think of an element of omega n is some small, you take the refinement of the partition level, n, 1 millionth. It says these are tiny, tiny little intervals, okay? And then you have the full branch, Fn. And if you think of the iterates, if you think of omega n and you iterate omega n once, twice, 3 times, right? And by the chain rule, you take 2 points here, x and y, right? And we're interested in Fn prime of x and Fn prime of y, and we want to compare the derivative, then by the chain rule, this derivative here is the product of the derivatives along the orbit, and this is the same here. Okay? So, because the derivative is not constant in each branch, these will pick up different derivatives, right? At every point, this will always be contained inside one element of the original partition. Remember, this is a refinement, and it has the property, if you remember full branch maps, that all its iterates up to time n. At time n, it will map to everything, but up to time n, it's always contained inside one element of the original partition. And so, imagine that you take Fn of x and y close to the 2 endpoints, and you iterate, and then, who knows, maybe you're unlucky, and every time the derivative on the left is bigger than the derivative on the right. Right? If you look at the images of these. And so this is growing exponentially faster than this, because even there might be a small difference, if the derivative here is always bigger than the derivative along the orbit of x is always a little bit bigger than the derivative along the orbit of y, then the ratio is the diverging, these two are diverging, right? This is always bigger, and therefore you fail the bounded distortion. Right? So the bounded distortion is telling you that this does not happen. Right? I want to try to, the bounded distortion is a subtle concept, and it takes a little while to digest it, but bounded distortion is telling you that this does not happen. So somehow, for some reason, you cannot have just constantly one side growing faster than the other. Okay, and we will try to see, okay, why this is true. This part of the reason for this proposition is not only to give us some concrete conditions, but also to help to do some bounded distortion calculations to help us understand better how this bounded distortion works. So we're going to start with the first condition there. So what do we need to estimate? So we choose n, we choose omega, and we choose 2 points x and y, omega n. Right? And then the bounded distortion says that we're interested in estimating the log of f and prime of x over f and prime of y. So the first step of the proof is almost trivial step, in which we use the chain rule again, right? And this is log of the product I equals 0 n minus 1, right? So fn prime of x is just the product along the orbit, right? So this is f prime in xi, where xi, this is x0, let's just call them x0, maybe y0, xi over f prime of yi. Okay, because this is a chain rule, you're just taking the derivative. This is just equal to the sum I equals 0 and minus 1 of the log of f prime of xi over f prime of yi. Now this is just the condition for n equal, it's just, look, what was the condition for n equals 1? It's just so xi and yi belong to same element of one of the partitions, right? Of not the refinement omega n, but omega n minus I, basically, right? But so xi and yi belong to an element of the original partition in particular, and so they satisfy this bound by assumption. So this is less than equal to the sum I equals 0 to n minus 1 of k. Okay, so I can take the k out. K times the sum of fx of fxi. Okay, let me write this as I plus 1 minus 1 I plus 1. Which I can just write as the sum as k and the sum I equals 1 to n of xi minus 1. Right? Because this is f of xi, f prime of xi over f prime of yi less than equal to k, f of xi, which is xi plus 1, minus f of yi, which is y plus 1. Everything okay? Yes? Okay, so we have, let me just summarize this because this is a key point. So log f n prime of x naught over f of n prime of y naught is less than equal to k, and the sum I equals 1 to n xi minus yi. Now what is this xi minus yi? So we have x naught, y naught, right? These are inside some element. These are inside some element omega n. Right? And then we are iterating them. And as we said, the images of this omega n stays inside one of the original partition elements every time. Okay? Anyway, we are iterating xi, yi, and then eventually we get to xn, yn, right? And xn, yn is inside the interval 0, 1. Right? Because omega n maps bijectively to 0, 1. Right? So this is also inside some element. So what are we summing here? We're summing the size of the images of this interval, right? So what this is here, sorry, this should be a 1, right? So from 1 to n. So we're looking at this 1. If we have 0, it doesn't matter, it's just adding an extra bit. But we're summing the size of these intervals. And what do we want? We're looking for a bound that is independent of n. Right? In fact, we're looking for a bound that will give k or some constant. Maybe I should have used, maybe let me use a different constant here. It's not going to be the same constant here. We want this to be bounded uniformly independently of n, right? Because we want the constant. And then we also want this size here to come at the end, but that's not so important, that will come out. The crucial thing is that we want this to be some bound independent of it. So how can we do that? This is a sum. Is this an increasing or decreasing sum? The terms, are they increasing or decreasing? They're increasing, right? This is getting bigger and bigger. You start with a small interval inside omega n, and then it is increasing. In fact, the map is expanding, right? It's increasing. So how can we hope to get this bounded independently of n? Any ideas? Can it be independent? Maybe it cannot be. What do you think? How can we bound this sum? We're summing up all these sizes of these intervals. So paradoxically, so what assumption have we used so far? We've used assumption 1, right? So here we've used assumption 1, but we have not used yet the uniform expansivity. In fact, the uniform expansivity seems to be working against us, right? Because it's growing. So here we have used here we have used condition 1. So this is a almost trivial step, right? Where we use condition 1, the kind of inductive assumption in some sense. And we get to this. And now we should use the uniform expansion. How do you think this can work? What does the uniform expansion tell us about what happens to this interval? So from here to here, it is fn minus I iterates. So when in doubt, let's say when in doubt, guess what? Chain rule or what did I say? No? Mean value theorem. You remember what the mean value theorem says? These are those theorems, you study them in calculus and you think, okay, this is obvious, what am I going to do with this, okay? Now you get your applications of the mean value theorem and the chain rule, and they're non-trivial, or at least they're useful. What does the mean value theorem say? The mean value theorem says that if you compare the sizes of this, then there is a point at which the derivative is the ratio of the sizes. Right? So the mean value theorem says that there exists some psi I, there exists some psi I in xi, yi, such that the length of this, so yn minus xn, is exactly equal to the derivative of n minus I times psi I times the size of xi minus yi. This is exactly what the mean value theorem says. Is that this is because this is the average derivative, right? The difference, the ratio between these, the ratio between this and this is actually achieved at some point as the derivative itself. And what do we know about this derivative? Now we want to use the uniformly expanding. Okay, now it still looks like it's working against us. Okay, but let's follow through because this is the only thing we've got. Okay, so so we know that this is greater than or equal to c e to the lambda n minus I xi minus yi. Here we use the uniform expansivity. Uniform. What this really says, if we kind of look at it backwards, is that this is small compared to that, right? So, of course, initially it says that this is big compared to this because we have uniform expansion, but what also this means is that it's small, okay? So, i.e., okay, in other words, it says that xi minus yi is less than or equal to c to the minus 1, e to the minus lambda n minus I, yn minus xn. And suddenly everything falls into place, right? Because then we plug this in here. Okay, so we said that we have the log of fn prime of x naught over fn prime of y naught is less than or equal to some k tilde, the sum I equals 1 to n of xi minus yi, right? And here we have a bound for xy minus y, which is less than or equal to k tilde times the sum I equals 1 to n of c minus 1 e minus lambda n minus I over yn minus xn. just less than or equal, which is just less than or equal to k tilde c minus 1, sum I equals 1 to infinity of e to the minus lambda I. I made it I equals 0 because when I is equal to n, this is 0, yes. So this is just from I equals 0 to infinity to the minus lambda. Okay? Yn minus xn. Okay, which we define as k. Yn minus xn. Okay, let's put this. So this here. So what is the magic here that is going on? How come we suddenly turned this uniform expansivity to our advantage? What is it that was looking bad but actually turns out to be good? How did we manage to get a series that is increasing to be uniformly bounded in n? Where is the dependence of n on n gone? Can anybody say? Tell me.
It's just that you're going backwards, so you're just like contracting. And I guess it's just the last term is like determines everything.
Exactly, right? So it is a kind of fake dependence on n. Or it's in some sense the point is that it's true that it's a series that is increasing and that this number of terms in the series depends on n, but the biggest term in the end does not depend on n, right? The biggest term in the end is fixed. And what is the terms that you're adding are the small terms right at the beginning, right? So when you take n very large, the extra terms that are here, they're not big terms, they're small terms. Geometrically, exponentially small, right? So there is an implicit of course, there is a dependence on n in this sum, but when n is very large, you're starting with very deep with very small intervals, and so you are, what we show here is that this is a geometrically decreasing sequence when you go backwards. And when you increase n, is you're actually going backwards, not forwards. So this is somehow the magic of this bounded, somehow the reason why you cannot get that accumulation that I was talking about, the accumulation of more derivatives on the left and the right is somehow just because you don't have time to do it, or somehow just because of this geometrically decreasing sequence. It's just that the distance between the 2 points is too small for this different derivative to accumulate. I'll be honest, I don't have an explicit heuristic answer for why, the situation I described does not happen, except for just this calculation that shows that it cannot happen. Okay, so this is the first one. Right? The others will essentially reduce in some of the steps to this one. So let me explain what we do for the others. So because here we've assumed condition 1 here, okay? So for condition 2, we're going to start with this first step here. So now let's look at condition 2 here. And we start with exactly what we have here. Log of fn x over fn prime of y is equal to the sum of the logs. But here we don't have a kind of inductive assumption. We just have the fact that it's C1 plus alpha. And how is that going to help us? Well, we're going to write it like this. We're going to write, first of all, that we can write this as equal to, less than equal, maybe equal to the sum of the logs of fi xi minus f prime yi over yi plus 1. So all I've done is just add and subtract f prime of yi over f prime of yi. Sorry, add and subtract f prime of yi and f prime of yi, and I get that. And then here, this is just less than equal to. So here we use a basic inequality that log of the absolute value of log 1 plus x is always less than equal to log of 1 plus the absolute value of x, which is less than equal to x. So you can check, this is just if you look at the graph of log of 1 plus x, you see that you have this, and therefore I'm going to write this is just less than or equal to the sum. Okay, let me write this. So this is less than or equal to the sum and minus 1 of f prime of xi minus f prime of yi over f prime of yi. Okay, so I'm just saying this is log of 1 plus something, and I'm using this inequality to say that this is just less than equal to this term here. And now I use that this is Hölder continuous. F prime is Hölder continuous on each branch. Xi and yi belong to one branch. So this is just less than or equal to the sum I equals 0 to n minus 1 times sum k tilde times xi minus yi to the alpha. Why can I ignore this denominator here?
Uniformly expanding.
Yeah, exactly. So it's uniformly expanding. So this is at least bounded away from 0. Right? It cannot be arbitrarily close to 0. So I'm including this in this constant, right? So I'm putting this in there's the Hölder constant, and I'm including this derivative here, which is bounded away from 0, whatever it is. And now, what do I do with this now?
The same as before.
Exactly. It's exactly the same as before, right? We just have an extra alpha, but this alpha goes in here, so it's going to come into the constant here. So we will get that this is we get an alpha exponent here and here, but sorry, here we get an alpha exponent. So we still get a uniform bound exactly as before. Okay. Then proceed as before. Bound. The sum as before. Okay, so this is the piecewise C1 plus alpha. So notice that here, this is again, I think there's several things that are not easy to really get a feeling for why this is true, because in some sense it's almost as though the only thing we're using is the uniform expansion, right? The C1 plus alpha is a very general criteria, and so we're not assuming that we satisfy for n equal 1, right? We're just assuming something on the regularity, but we're assuming that the C1 plus alpha is uniform for all branches. This is an important thing. And then somehow this regularity with the uniform expansion is enough to get this property. Okay, so the last bit is this is the C2. So we also, the first step is also exactly the same as before. So we also start just by writing this, let me write it again. Fn x over Fn over y naught. So it's just equal to sum I equals 0 to minus 1 of the log of f prime. Actually, what I want is yes, so I'm going to start right from here. I'm going to use all the way up to here is general. I don't use any assumptions here, so I'm going to use this is the sum I equals 0 to n minus 1 of f prime of xi minus f prime of yi over f prime of yi. So even though, as we said before, this is bounded away from 0, but because even though we have assumed now that the map is C2 on each branch, right, this does not allow us to use this Hölder bound for this, right, because the C2 still means that the second derivative could be arbitrarily large, and we don't have any quantitative bound on this, like having the Hölder continuity. So we're going to need to use somehow this, that's what this is in some sense. It's a condition that relates the first and second derivative and is going to take the place of the Hölder continuity. And so we're going to use the mean value theorem again, twice. So by the mean value theorem, we're going to use the mean value theorem both for the first derivative. So the mean value theorem for the first derivative tells us that there exists two values, xi and eta I, in the interval xi yi, such that one of them says that f prime of xi minus f prime Okay, this is the mean value theorem applied to the derivative, right? So the difference between the derivative is given by the derivative of the derivative in some intermediate point, which is the second derivative. And also we have that f of xi minus f of yi, this is a standard mean value theorem, is equal to f prime in eta I times xi minus yi. Okay, and what I'm going to do is I'm going to actually substitute this in, I'm going to substitute this into here, right? So this is f of xi minus f of yi over f prime, okay? So this implies here that we have the log of fn prime over 0 over fn prime over 0 is less than or equal to sum I equals 0 to n minus 1 of, so here I'm going to substitute this f double prime psi I, so this is f double prime psi I over f prime of yi times xi minus yi. Okay, but then I'm going to substitute, okay, let me just write it here. So this is equal to the sum I equals 0 n minus 1 of f double prime psi I over f prime of yi times f prime of eta I times f of xi minus f of yi. Okay, so far? Yes? So, all of that is to these two substitutions. And now here I have this is bounded by whatever this supremum is, right? Because this is the supremum over all possible x and y for f double prime over f prime squared. Okay, so the fact that we're taking f prime in two different points in the interval doesn't matter, because you can just take the worst of the two. You can bound this by the worst times itself, right? So this is less than or equal to some k tilde. This is condition 2. This is the assumption. And then we have, again, exactly the same situation we had before that. So we have a constant times the sum. This is just xi plus 1. Here I can just put I equals 1 to n, and this becomes xi minus yi. And then as above. Okay, again, this is now a constant. That's what the assumption says, is that this is the supremum over all the intervals is finite. The way I could have said it is just that this is less than or equal to some constant over all the intervals in P1, over all xy, right? So this interval here, xi, yy, is inside one of the elements of the original partition P1. So in particular, this is uniformly bounded by some k tilde given right at the beginning. Okay, and so we get the sum, and this is just as sum as above. So once again, we use the uniform expansion at the last step, right? So in all three cases, we end up with just having to sum this series, right? So in all three cases, we reduce the situation to one in which we just need to bound this geometric series, and that's where we use the uniform expansion. So each of those conditions is used to reduce the problem to this and then we use the uniform expansion for that. Any questions? Okay, so once again, please look at this, and it's really worth spending a bit of time digesting these calculations as we go forward. We leave it as an exercise to check that the Gauss map satisfies bounded distortion, okay, using this proposition. And you can see, of course, also if you take a piecewise affine map and you just take some small perturbation where the derivative remains bounded, then it will also satisfy bounded distortion because it will belong to condition 2. So this is a large class of maps that actually end up satisfying bounded distortion, and therefore, by the main theorem, which we'll prove tomorrow, have a ergodic invariant absolutely continuous measure. Right? And in particular for the Gauss map, we already know what this measure is, so that theorem gives the ergodicity of that measure. Right? So the fact that the Gauss map has bounded distortion means that that measure is ergodic. Right? Okay, thank you very much. Yes, Ricky.
Do we need uniformly expanded? Because we need a unit only that it's bounded on the law. Like uniformly bounded doesn't have to be fused with each.
For this sum, you mean?
Yeah.
Well, for this sum, you need this sum to be uniformly summable.
Yeah, I mean, uniformly expanded means that it's Fn prime is bigger than C exponential 1 by n. But I think it would work even if we take just C or something. Like that n is not bothering us.
It is, because if you take just C,
Because the n was helping us, we disregarded it or something. When we inverted it.
sorry, you mean if the derivative is just uniformly bounded below by something bigger than 1?
Yeah, it doesn't depend on n.
No,
Maybe not even bigger than 1.
no, it does, because you need to have a geometric sequence, right? I erase that now, but when you do the backward, when you look at these, you need each of these to be exponentially smaller in n. If each of these is just less than half of this, when you sum them all, you don't get something convergent, right? If you just have a fixed bound, then you can say, okay, each of these individually is less than half of this, but then the sum of them might still diverge. So you really need them to be not exponentially, but somehow you need to be summable in a uniform way. Yes. Okay, thank you very much. See you tomorrow. See you for spinning.